is less than or equal to mi minus 1. So you're looking at the previous I minus 1 elements. You're looking at what's the max. And if you are, at that max or below, we're going to count q to the wi minus 1, and then it's going to be 1 otherwise. So wi strictly greater than that. In fact, that you actually know because it's a restricted growth word, this actually has to be then this value plus 1. So using this, we can actually generate the q-Stirling number of the second kind. So let's go back with this weight. Okay, so let's see. So here I have a weight 1, it's nothing new here. This is strictly bigger than the previous max. Up to here the max is 2. And then you say, oh, well, this is actually equal to the previous max, so it's going to be q to this entry minus 1. So I get a q to the first. Same thing here. The max to the left is 2, so I get another q to the first. So overall, I'm going to get a q to the second with that element. Maybe for time, I'll just write these in, otherwise we'll be here all day. Anyway, if you compute the other ones, q to the first, q to the first, q to the first, it's the same. 1, 1, 1. And then we sum these up, and we get q squared plus 3q plus 3. So this is q-analogue of the Stirling number as equal to. So I know I did a little bit fast, but there is a statistic. I should mention that there are many, 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 many statistics that generate q-Stirling numbers of the second kind. Just to mention some references. Let's see. So other statistics. Due to Garcia and Remmel. Who else? Walks and White. Walks and White have lots of statistics, not just one. It's many. In fact, this statistic I described is very, very close to a statistic they call the LS statistic. In fact, they actually do this computation for every element. They don't have this case. So they always just take whatever your entry is and minus 1. So the difference is going to be just a factor of q to the k choose 2. And then who's the other one? I forget. Don't remember. Oh, Mill. Okay. All right, so now we're back to the goal, which is we want to find a subset of RG words, and we want to find 2 statistics which can actually generate this. So that's the next thing we want to do. So what we need is something called allowable RG words. So allowable RG words. So I'm going to state it schematically, I guess. So, allowable RG words. Denote this as script A and K. So this is going to be a subset of these RG words. And they look like the following. So they have to follow the RG word description. So you know it's going to start with some 1. And then at some point you get a 2. So it'll be some 1s and then a 2. And then you have some other elements here. So you could have 1s, you could have 3s, but then you have a 4. In fact, you have to have a 3. Here by the standardization. You're forced to at least have 1 3 here, and then whatever else you have. You can have 1s or 3s. And then the next piece, you can have 1s, 3s, 5s, and then a 6, etc. Okay? So notice here that the way the pattern goes is that I think of it as the no ballet rule. I like to think of like no 2 2s. So notice I can never have 2 2s, right? Or more. And so that's a good way to remember. It's a stupid way, but anyway, it's the way we remember it is. So okay, so that means going back to these words, we have quite a few RG words that have many 2s. So this is going to get thrown out. This gets thrown out, thrown out, thrown out. In fact, we only have 3 left. So that really reduces things considerably. Huh?
Why did we eliminate the third one?
Third one? Oh, because it has 2 2s. Very bad. No ballet. Sorry.
So is it that you only guys have, for every even number, that number's only allowed to show up once?
Here's once, and it's an increasing, and this RG condition always happens the first occurrence of an integer. If you look at the first occurrence of 1, 2, 3, 4, etc., that's increasing in the word. So that's part, that comes again out of the standardization. If we didn't have that, that would be much, much harder. Okay, I need a weight. So, let's put it over here. So, the prime here, here. This is going to be the same. This is going to be a little bit different. So, q to the wi minus 1. So, when we have strictly less than, we're going to pick up a 1 plus q. When we have equals, we're going to have q to the wi minus 1. And then 1 is going to be, I'll just write down OW otherwise. Okay? So the whole point is that we're going to pick up 1 plus q powers in certain conditions. So let's see if we can do this over here. Okay, so let's look at this. Great. So notice we don't have to do these. Okay, so over here, we get a q to the 0, we get a 1. Here, you say, okay, well, this occurred before. The local max is 1. So then we're going to have a q to the 0, and then we pick up a 1 plus q. So 1 plus q. Oops. This is going to be here. 1 plus q. And then over here, we also get another 1 plus q.
Shouldn't this be ones?
Huh?
Shouldn't this just be ones?
No, because what happens is you look at the local max. Local max here is 1. Here, local max to the left is 1. But this is... oh, yes, you're right. This should be ones. You're right. I stand corrected. These should be ones. Yeah, because it's equal. Equals, and then this is greater. So this is going to be ones. Thank you for the correction. So again, here, similar. This is bigger, we still get 1. This is going to be the first one. We're going to pick up a 1 plus q. And then over here, we're going to get a 1 plus q and a 1 plus q. So I'm doing it fast, but again, if you multiply this out, you really will get q squared plus 3q plus 3. So we get the same thing. So theorem, right over here, somewhere. Is the q-Stirling number of the second kind can be written as this weight over the allowable words. And again, I didn't write it out, but very easy to split the statistic up into 2 pieces, the A piece and the B piece. You can see picking the right powers. Here we pick up a power for the B statistic. In this condition, pick up 1. Otherwise, it's wi minus 1. So it's easy to see that split, so I'm not going to write this out. Okay, so we have this. So if you know me, I like to look at partially word sets. So already this is a beautiful enumerative result. I want to do something more. I want a partial word set. So let's start with that. And even before that, let me say something about Stembridge's q equals minus 1 phenomena. I should actually do that now while I have all this data here. So Stembridge has the following result. Let's keep this up here. Okay. So he says the following. So suppose you have a set E that's finite set, and then you have some kind of counting function over the set. So it's a q-analogue. So I'm writing it this way. And then he says, okay, let's set q to be minus 1. And if you do that, what's going to happen is that there's some sort of natural involution that's explaining what happens when you set q to be minus 1 in here. So this is counts, and this is what I'm trying to do, is counts fixed points with respect to some involution. So you could ask with q-Stirling number of the second kind, what happens when we plug in q is equal to minus 1? What does this actually mean? And well, now that we have this interpretation with powers of q and 1 plus q, you see that the only time that we pick up these, if you set q to be minus 1, any term that has a 1 plus q in it is just dying. So what that means is that the only allowable RG words that survive are the ones that are going to be weakly increasing. So we have sequences of 1s, then a 2, sequence of 3s, then a 4, etc. So then we have that result. So stateless, I don't know what to say.
This result is just for the Stirling numbers, or is it more general?
Well, this is a general statement. He
So
says,
what's the condition on the weight for that?
this is just being high-mindedness, saying, okay, suppose we have a q-analog and we plug in q to be minus 1. Whatever's left, there's some involution, and fixed points, there are what's left. Assuming they all have the same sign, and sort of hiding some things.
So it's a phenomenon, it's not a theorem.
No, it's a phenomenon. And he's had a few papers where he talks about this.
It happens a lot.
It happens a lot in combinatorics, sure. So again, we can actually see that if you take the q-Stirling number, set q to be minus 1, then we get the number of weakly increasing allowable words. In script A and K. So again, it looks like a bunch of 1s and a 2, a bunch of 3s and a 4, etc. Okay, now we talk about posets. Okay, so we have not much time. 48 minutes? Oh, okay. I mean, not 48 minutes. Give me a time. You giggle too much. I'm sorry. We're having too much fun. So let me say something about the Stirling poset of the second kind. So we want to take these RG words and form a partially ordered set. So let me just write it. 1, 2, 2, 2, 1, 2, 1, 2, 2, 1, 1, 2, 2, 2. So this is a very easy example. And in fact, I actually have a matching here too. If I had colored chalk, I would have done this, but I hate colored chalk. Okay, so these arrows, if I had time, I would say something about how these elements are matched. But this is actually the matching that goes on when you set q to be minus 1. That things will go away, and then this is your fixed point when you set q to be minus 1 in the original Stirling number. Okay, so then looking at this poset, you can see at this level, these are the usual weight. These are all the words that have weight 1. These are the ones that have q to the first. These have q to the second. You can see how you move up from an element, going from one element to another, as you read along, and then you just increase one of the entries by 1. And that actually bumps up the usual weighting, not this other weighting I did with psi. So what we actually show, first thing, is that we can actually decompose, and again, this is an easy example, this poset into Boolean algebras. So we can actually say, what are the Boolean algebras? The minimal elements are going to be allowable words. Typically, this is not so easy. These are huge posets, and these Boolean algebras go up. And where they go up, so for example, this little Boolean algebra corresponds to the 1 plus q squared. That if you multiply this out, this actually is giving you the rank generating function of these elements. So these numbers are actually telling you what are your Boolean algebras. And if I had a q power in front, that tells you how much you lift the Boolean algebra in the poset. So that's a theorem. I won't write it. Then you can start asking about we've got this homological q equals minus 1 phenomena. So this is due to Hirsch, Shereshian, and Stanton. They have a homological q equals minus 1 phenomenon. So the idea is that you have, what it boils down to is that you have a complex, you're using the elements of each rank to be vectors. You have a boundary map going from one level to the next, and it's truly a boundary map. When you go 2 times, it is 0. And what happens is that if you're in a good situation, this q equals minus 1 phenomena is actually an Euler characteristic computation, and we're actually computing homology. So I don't want to say too much about this because Duran hates topology, but anyway, moving right along. But what we can do, there's something called algebraic Morse theory. I can do Morse theory and collapse things and actually show topologically this result about what happens when you set q to be minus 1. So I'll leave it that way. Okay, I promised to talk about q-Stirling numbers of the first kind. We'll do this very rapidly. Here they are. Here's a recurrence. De Medici and Leroux showed that we can actually realize q-Stirling numbers of the first kind using rook placements on staircase boards. So I've done an example. Here we are. So these are rook placements. So to find C42, I'm going to need staircase boards. Looks, I guess, upside. I guess this is French notation. French is, I shouldn't say French. Upside down. Okay, and so we have 2 rooks for this, and the condition on the rooks is you can't have more than 1 rook in a column. So, and then the statistic q to the s of t, this is, I call it the south statistic. You count number of squares below rooks. So here's 3, q to the third, here's 2, q to the second, etc. So then the question is, can you find a subset of these boards which will generate the q-Stirling numbers of the first kind? And the answer is yes. If you play checkers or chess, you're used to seeing shaded boards, checkered boards. So if you start shading these boards from, this is not shading, and along anti-diagonals, you notice that only some of these boards actually have rooks on the shaded squares. So this is an example. If you were to shade this, perhaps this one works. Not that one, whatever. I think there's 2 more. This one. Is that it? Maybe this one. Maybe this one too.
Oh, yeah.
I think that's it. And so then there is a statistic where we can actually realize this. So again, we have the south statistic, and then this R of t, q plus 1 to R of t. This is going to count number of rooks which do not appear in the first row. So for example, here we still have q squared, but then it's going to be 1 plus q to the first power because there's 1 rook not in the first row. Again, we have a poset in the background, Sterling poset of the first kind. This has a Morse matching, decomposition. We have this algebraic complex supported by a poset, and we get basis for homology. Orthogonality, so we have all the same sort of stuff here. Orthogonality, there's a sign version of Stirling numbers of the first kind, just stick the sign on them. Classical result of de Medici-Leroux is that these are orthogonal polynomials. And it turns out that if I replace this 1 plus q with t, and the same thing with Stirling numbers of the second kind, where we sort of 1 plus q replace it with the t, you get the same sort of results with qt. And these are combinatorial proofs. You're actually nice bijective proofs. You're actually working with the object. So this is with myself and my student. That's all I have to say. That's all my time. Goodbye.